Let's start our discussion of capacitors by describing their construction. A capacitor is two metal plates which are separated by an insulator. This insulator is called a dielectric. Obviously, because there is no conductor connecting the two plates, no current can flow between them. Practical capacitors need rather large plates, and so they are often rolled up and put into a can. Different capacitors can be made with different dielectrics and also with somewhat different construction. These also have somewhat different performance. If you exceed the maximum rated voltage for the capacitor, it will spark through its dielectric and possibly destroy itself. In old books, capacitors are sometimes called condensers. So let's see what happens when we connect a capacitor to a battery. Electrons from the negative terminal flow into the attached plate, giving it a negative charge. This pushes electrons out of the opposite plate, giving it a positive charge. If we now disconnect the battery, the capacitor will retain this charge until we touch the two wires together and so discharge it. A capacitor is therefore an energy storage device. However, unlike a battery, it can only store a small amount of charge because it has no way of replenishing its electrons. In a battery, they are replenished by a chemical reaction. The bigger the capacitor's plates, the more charge it can store. We measure capacitance in farads. This is a rather large unit, and so it's more common to come across microfarads, nanofarads, or picofarads. The capacitance is defined as the charge stored per unit voltage that you put on the plates. C equals Q over V. So let's see now in more detail what happens when we charge a capacitor up. In this discussion, we'll put a resistor in the circuit to represent the resistance of the wires, or an external resistance. This turns out to be quite important. As soon as we connect the battery, electrons start flowing into the capacitor, and therefore its charge and voltage starts building up. As the voltage on the plate gets higher, electrons find it more difficult to flow into the negatively charged plate because the electrons already on that plate repel the new arrivals, and so the rate of build-up of charge decreases, and eventually the voltage on the plates approaches the battery voltage connected to them. Now let's think about what's happening to the current at the same time as the voltage is increasing. Initially, when the battery is connected, there's a rush of electrons into the plate, in other words a high current. However, this drops off as the plates get full of charge and further electrons are repelled. So as the voltage is building up on the plates, the current drops down. When the capacitor is discharged, exactly the opposite happens to the charging cycle, and the voltage disappears from the plates. Now, the speed at which a capacitor charges and discharges depends on two things. Firstly, on the size of a capacitor in farads. Obviously, the bigger it is, the more slowly it will charge because it requires more electrons to charge up the plates. The second thing it depends on is the size of a resistor, because the larger the resistor is, the more it will reduce the current flowing into the plates and the longer the charging process will take. The formulas and equations are shown in the diagram. You'll notice that the term R times C appears in both the formulae, and this is known as the RC time constant. The value RC itself gives the time taken for the capacitor to charge to 67% of its final value, or to fall to 33% of its final value when it's discharging. This gives us a clue to the purpose of capacitors in DC circuits. They are often used to provide timing and delays by devising circuits which trigger once they have charged up to a set value. A very popular integrated circuit, that is a silicon chip, which uses this principle to generate all sorts of useful timing signals and waveforms, is called the 555. In the next video, we'll consider the capacitor in AC circuits.